This is the unboxing and setup of the CN0566 or phaser kit. So opening the box for the first time, under our first layer, we've got an SMA cable and our first bag of accessories. So in the accessory bag, we have a spare USB cable. We have a power cable for our microwave source and an HB100 microwave source itself. So we'll talk in a lot more detail about this shortly, but it's basically a motion sensor, and it continuously transmits about 10.525 gigahertz. On our next layer, we've got the Raspberry Pi power adapter. And on our final layer, we get to the phaser itself and our second bag of accessories. So in the second bag, we've got a Vivaldi antenna from WA5VJB. So it operates from 5 to 18 gigahertz. We'll be operating right about in the middle of that. And finally, a tripod for mounting the phaser board. Okay, and then finally, we get to the phaser assembly itself. So be careful removing it from the bag because it has standoffs mounted to the corner of the board. Okay, and the first thing to do is to connect this USB cable. So the USB cable ships unplugged so that if it gets if it shifts around in shipping, it doesn't get damaged. So we're going to plug this into the center connector of our Pluto until it snaps. And these standoffs are for experiments where you set the phaser board horizontally on a surface and apply and aim the microwave source down at the assembly. And we've also got this tripod mount, which is probably a little more common for tabletop setups here. So we'll take this tripod and extend the feet first. And be careful, these don't lock. They're pretty stiff, but they don't lock in place positively. So so they will compress back in if you press on them hard enough. And we'll tighten this to the first order. Okay, and then as you're installing the tripod, you want to be gentle with this. In the interest of simplicity, the camera mount is screwed right to the circuit board, so we don't want to put too much stress on that. Then also make sure we don't pinch this little U.FL cable here as well. So fairly straightforward, just watch out for those couple of things. And then tighten that finger tight. And then double check the tightness of the nut here, or hang it upside down if we want gravity to help us out. Okay, and then spread the feet. There's our phaser setup. Okay, so the next piece, let's talk about the HB100. So the HB100 does not come with any sort of convenient way to mount it, but a couple of, almost anything will work. So if you have a little tabletop vise that can clamp the bottom edge of the board here, the bottom corner of the board, that'll work fine. Or another option is this tripod here comes with a selfie camera mount that is a perfect fit for the HB100. And finally, we provide a, there's a step file on the wiki page that you're probably looking at right now for a fancy HB100 holder. And to that, you can use a 3-cell AAA cell battery holder here. So we can turn on our HB100. And when this second light comes on, you can see that the light blinks as we move a target toward and against it. To power the HB100 in the absence of a battery holder here, so it does come with this cable here. And probably the easiest option for powering is to take an old USB cable, and you can either cut the cable and wire directly, or in my case, I've put little breadboard jumpers onto the side here. So we'll take the positive into the center conductor, the negative onto the outside conductor here. Then we'll plug this connector into the HB100, which is polarized, so it only goes in one way. Okay, and then we will plug it into a USB power source. And sure enough, it comes on and works as advertised. So there's our second option for handling the HB100. Again, this is super handy for getting up and running. For more controlled experiments with radar, we'll use the antenna where the phaser board itself provides the microwave signal. For mounting the Vivaldi antenna, again, a little desktop vise will work just fine, but another option that works really well is to take a second tripod with a fender washer and a 1/4-20 nut and just clamp the lower edge of the antenna, making sure that we're far from the edge where we might actually affect the RF performance. So finger tight there, and we've got a nice convenient mount for our Vivaldi antenna. For powering up the board, one thing to note here is there is a USB-C connector on the Raspberry Pi that we are not going to use. We're going to use the second USB-C connector that's on the phaser board itself. So we'll plug that in, and again, being careful not to put too much stress on the board. Maybe put pressure from the top until that snaps, and then the next step will be powering up the board itself. Okay, so here we're going to go through the setup and first boot and calibration of the phaser assembly here. So we're going to start out on this web page, and the first thing that you'll notice is that we're actually going to have to re-image the SD card that came with the first build of phasers. So there's a couple of ways to do that, a couple of tools that you can use, but we're going to go the easy route here. So the first thing that we need to do is grab the Kuiper Linux, Analog Devices Kuiper Linux image. And I've got that tab opened here. And the release image is at this link. Okay, so you'll want to download this 2021 R2 release image file. So this is a big zip file that you then unzip and then load into the imaging software. For the imaging software, we have a custom imager that is in development right now, but for the moment, the Raspberry Pi standard imager will work just fine. So we have selected the use custom image, and we've selected the 2023-0402 Kuiper image.img unzipped file here. Okay, so we're going to, with that image selected, we will choose our storage. So I don't have any storage in here right now, so I'm going to insert an SD card. Okay, shows up nicely here. And so then we're just going to click write. So yes, we want to erase everything and start with a fresh image. Okay, so with the image written, we're going to come over here to our phaser board itself. And pretty straightforward, there's only one place an SD card can go, and that is into the Raspberry Pi slot here. Once the SD card is in and the system is booted, the first thing we're going to have to do is some setup operations. And of course, we're going to want to run software on the board as well. So there's a number of ways we can do that. We can either run software directly on the Raspberry Pi with a connected keyboard and mouse, or we can use a virtual connection, and we're going to show you how to do both. So in addition to the SD card, I'm going to plug in a micro HDMI to HDMI cable, and I'm going to put this into the connector. There's two HDMI connectors. We're going to use the one closest to the USB-C power input. Okay, be careful, plug straight in and grip firmly from both sides. And you'll notice that my monitor shows, yes, something has been connected. Okay, and also so we can have local control, I'm going to plug in a little keyboard / trackpad so we can operate everything directly on the local Raspberry Pi. Oh, and so we can connect remotely, I'm going to, we can use either the Raspberry Pi's wireless network or we can use a wired connection. So I'm going to use the wired connection because it sets itself up pretty reliably here. And with that, we're going to take the power adapter and plug it in. Okay, so we get the Raspberry Pi boot screen. The first thing a freshly imaged SD card will do is resize its file system. So the image is a certain size. If the SD card is larger, by default, Kuiper Linux will expand the file system to use the entire card. Okay, we're going to give this a minute to boot. Okay, and we have a cursor. Let's make sure our keyboard is on. And you'll notice we have a mouse pointer, and we can use our little start key to bring down a menu, and we've got full control over the Raspberry Pi here. Okay, so while the camera is okay, and maybe we can see some things on the screen here, what I'm going to do next is establish a remote desktop session here. So to do that, we're going to use the Real VNC viewer here. So it's a freely available program, and we're going to type in analog.local. Okay, and that brings up a password prompt. The password is analog. Okay, so now we've got the same desktop that we're seeing on the camera. We've got the same thing over reflected on a screen that we can capture with a lot more fidelity here. Okay, so we're going to ignore the camera now, and we're going to run our configuration scripts. Okay, so we can pull up a terminal here, and we're going to show you another way of connecting to the Raspberry Pi. So the VNC is useful for running scripts, graphical scripts directly on the Raspberry Pi. But if you're going to be working entirely remotely, then another thing you can use is PuTTY. So PuTTY is Realterm or your favorite SSH client here. So we can do the same operations we're about to do by connecting over PuTTY. So we'll connect to analog.local. Okay, and that gives me a security alert. We're going to accept that, and we've got a terminal window here. So we'll log in as username analog, and password, of course, is analog. Okay, and I guess we can run our commands. We can run our commands either through the terminal here or through the graphical desktop. So let's go back to that graphical desktop, and we'll go to the wiki page that we're on, the Phaser wiki page, the quick start page here. And we've got instructions for configuring the SD card. So let's go ahead and run those. So the first thing that we need to do is grab a configuration script. And going back and forth on where to run these, let's run it in the terminal here because it's easier to see. Okay, so we're going to copy this. And then we'll paste and run. Okay, perfect. And then we'll ls to list, and you see that we've got Phaser SD card set up. We have this script here. So the next thing we need to do is sudo chmod +x. So we're going to make this script executable, ph, and then hit tab. Again, the password is analog. Okay, and then we're going to /ph, and handy Linux tip, just type in the first couple of characters, and if they're not ambiguous, you can hit tab and it will bring the entire setup up. Oh, and we need to do, I guess we can just run like this. Okay, and then it's asking for the password, again, because it's running some of the internal commands as root, and we're just going to give this a minute to run. So it's doing a number of things. It's grabbing a copy of the latest Python scripts, which are in a development branch. It's configuring the boot process telling the Raspberry Pi that a phaser is connected, the ADAR 1000 devices, the synthesizer, etc. And another thing that we'll point out on the camera here is that there's a button and an LED, and we'll notice that there's no activity on the LED. So we're going to see how that changes in a minute. Shut off our screen here to give us a nice background. Okay, so after a couple of minutes, we've run the boot scripts here, and we actually get a little note here. So done setting up SD card. A reboot is probably in order, or definitely in order. So we're going to sudo reboot. And there's a hint on here on how to disable the desktop if you're only going to be communicating with the Raspberry Pi remotely. So we won't go into details here, but just know that there's a few different things we can configure here. So we'll type sudo reboot. Okay, and then after rebooting, we should have a fully functional phaser board set up. We can now, so the last time we connected to the phaser board, we connected to analog.local. One of the things the setup script does is it changes the host name to phaser.local, or phaser, and we can access it by phaser.local. Okay, so we're going to type the password. And that's just to help keep things straight. If you've got multiple boards on your system from analog devices, now this board is distinguished on the network as phaser.local. Okay, so the next step is we're going to run some scripts to find the frequency of the HB100 and calibrate the array. Yeah, so we have an HB100 here that is that's mounted to a tripod. So we're going to turn this on. And the board has stamped on it 10.525 gigahertz. That is approximate. So we need to find out what the frequency is exactly. Even if it was exactly or close to exactly the frequency that's printed here, the phaser board itself, the reference oscillator, has its own tolerance. And I'm going to point out one other thing while we're here, and that is the fact that we now have a heartbeat LED. So that's another way of telling that your SD card has been configured properly. And then the button here is for shutting the system down. So we'll talk about that in a minute as well. Okay, so here we're going to aim the phaser array at the HB100 and put it, approximately a meter away. We're a little bit closer here, but dead center along, facing directly at the array. Okay, and then we'll open up a terminal. And we're going to cd into pi-ADI. And again, if things are not ambiguous, you can just type the first couple of letters. So pi, and then tab, and then examples, EX, tab, and then phaser, PH, tab. And now we're in the phaser example directory. And if we list the examples, we'll see we've got a number of things in here. We've got phaser examples, we've got phaser functions, phaser GUI, but the one we're going to use first is phaser find HB100. So Python, this is a Python script. So Python PH, and of course it's not ambiguous now. It is ambiguous now, so we'll type PH and then tab. Now we'll type FI and then tab out to find HB100. Okay, so now the script is connecting to the attached devices. Okay, and sure enough, it says, hey, I think I found a frequency out here at 10.4 gigahertz. And the thing to look out for here, this is a complete sweep of the available spectrum on the phaser board. And if you see a single prominent spike, then that is the HB100. So if you had a lot of interference or multiple tones, or if something goes wrong, you wouldn't see a single prominent spike. But we do see a single prominent spike, so we're going to close the plot, and then yes, I'd like to save the calibration file. Okay, so at this point, let's run the GUI. So Python ph and then gu GUI.py. Okay, and here's our initial pattern. So look at this. We've got and we can click auto refresh. And boy, you know, that looks a little bit squishy, doesn't it? And if we look at it on a polar plot, maybe things look a little bit better, but it's certainly not a pattern by design. And the reason that that's the case is if we look at the initial output, we notice that we don't see a gain calibration or a phase calibration file. So the array isn't calibrated. We haven't done any adjustments to account for manufacturing variations and channel-to-channel variations here. But we let's get a rough idea of whether, let's convince ourselves that it's operating at all. So I'm going to take the HB100 and move it around. Okay, and sure enough, we see that the direction of the signal changed. We can come around to the other side. Okay, so we've got something going on here. It just doesn't look very pretty. So let's take care of that. So we're going to set the HB100 right in front of the array. I'm going to close the program. Then we're going to run Python phasor examples. And then we're going to give it an argument of cal. And that will run our calibration utilities. Okay, so we have some instructions here. Place antenna at mechanical bore site in front of the array, then press enter. So the first thing it's doing is it's calibrating, it runs a bunch of calibration routines here to measure the difference between the 8 array elements. And we get some useful information here as well. So here is, with that single tone coming in, this is kind of interesting to look at. So we can zoom in on the spikes here, and we see that each channel has its own gain, and we're going to compensate for that in software. We're going to measure this difference, and we'll compensate in the phasor software, or in the GUI. So we close that, and the next thing that we're doing is we're calibrating the phase difference between each element. So ideally, if all elements are illuminated with the same plane wave coming in, we should see no phase difference between elements. But we don't see that. Of course, we have some difference between the elements. So we're going to measure that and compensate for it. And here what we see is what we're doing is we hold one element at phase 0, and then we sweep the adjacent element in a circle, or 360 degrees. And typically you'll see that one of the readings is farther off. And this is where one element is on one Pluto channel and the other element, the adjacent element. So between elements 3 and 4, or 4 and 5, depending on where you start counting, you'll see a greater phase delta. But that's not a problem. We just measure it and compensate for it. Okay, so we've saved our calibration constants. We'll hit the up arrow twice so we can run the GUI once more. And let's see how our pattern looks. Well, that certainly looks a lot nicer, doesn't it? So we've got a nice sync 1 pattern. Looks like we're a little bit off center here, but if we go over to the polar plot, wow, now that looks nice. So let's wiggle the phasor board around a little bit, or I guess we should click the button to auto refresh data. Okay, so that should continuously take data. So we'll move the array around. See how things move around there. Okay, back on mechanical bore site. And we'll move the microwave source. Okay, so now we're all set. We've got a working GUI, we've calibrated the array, we've configured our SD card, and the last step is to shut down. So we're going to close the program here. And this is a persistent Linux system with an active file system on the SD card. So in general, you don't want to pull the power cord on a system like this. You want to shut down properly. So if you've got a keyboard connected, you can log out and click the shutdown button here. A little quirk if you're running a VNC server. So for some reason, Raspberry Pis don't like to shut down if a VNC connection is established. It thinks that something's going on and it will hold off and not shut down fully. So what we're going to do instead is we're going to close our VNC connection, quit out of this, and we're going to use the shutdown button on the board itself. So we're going to click this little button on the side here. This LED stops blinking. The light on the side of the Raspberry Pi will blink steadily for a couple of seconds and then stop blinking. So at this point, the system is completely debooted and it is safe to pull the power cord.